Run away with me.
Thank you very much. Thank you very much. I hope you're having a nice day, and I hope the day will continue to be very nice. Actually, it works perfect that I'll be talking right after Faradin, because he's been talking about disruptive technology. He showed you his slide ruler, and then he talked about the calculator and then the cell phone. So truth of the matter is, the computing technology that we've been developing since 1947 has completely disrupted our world. Right? Back in the days, our computer were the size of a gymnasium, and they were barely more powerful than a pocket watch today. And then we went to the personal computer, then a mobile computer. Now we have those cloud computing that nobody knows really what is going on. But we've been doing extremely incredible advances in innovation that essentially are powering our world today. So I was just Googling a few minutes earlier. Turns out that about 6% of the global economy relies on information and computing technology. So that's a very important part of our world. But we have to realize that everything we have been doing so far is based on the same principle. Our computing technology, although we went from those big-sized computers to the very small one to the very powerful one, they have not fundamentally changed. And what I mean by this is that they essentially all work the same way. It's bits and bytes and logic. We just got extremely smart at using them in a better way. We got very good at creating the hardware smaller and smaller and smaller and faster, but fundamentally, we're still doing the same thing for the past 70 years. So this is what I want to talk about today. I want to talk about a disruptive paradigm shift in computing technology. So we're no longer going to start using bits and bytes, but we're going to start using quantum mechanics. So for those of you who may not know what quantum mechanics is, it's the world of atoms and molecules. Because turns out when you go to the fundamental building block, I call them the Lego block of nature, they don't follow the same rules that we do. They behave in a radically different way. So quantum mechanics has been developed for the past 100 years. It was a crazy idea early on, but as advanced in science, as we kept on going with science, we realized that this was an incredibly precise theory. Not only incredibly precise, it's the most precise theory of nature that we have today. Every time we try to prove it wrong, we completely fail. So quantum mechanics has already given us great technologies, like the laser. The laser really changed our world. The laser, now we have laser eye surgery. We have, for those of us a little older in the crowd, the CDs and the DVDs and the Blu-rays. Now we don't use those anymore. But it was like, a real change. Oh yeah, the laser gave us the internet. If you don't have lasers, you don't have the internet. And the laser, L-A-S-E-R, light amplification by stimulated emission of radiation. That's a quantum process. Also, what did quantum mechanics give us? The MRI machine, magnetic resonance imaging. This is all based on quantum phenomena that happens in the proton inside your body. It also gave us the transistor. The transistor was the tipping point of computing technology. All of those technology relies on quantum mechanics, but they relies on what we call ensemble effect of quantum mechanics. So they don't rely on single atom or single molecule. Quantum computing is this next step. Is now we have the technology to be able to control the behavior of atoms, molecules, photons, small nano electric circuit, and then we can make quantum mechanics work for us. This is the field of quantum information, and today I'll specially talk about quantum computing. So as I was mentioning, quantum computing is a shift in the way we compute. So for the past 70 years, doesn't matter what kind of program language you're using, doesn't matter if you do artificial intelligence, if you program in Python, in C, or if you just use an abacus, at the end of the day, what you do is you work with zeros and ones, and then you manipulate your information using logic, so AND, OR, XOR, and so on and so forth. So the rules haven't changed. We just got better at using the rules. What we do with quantum mechanics is we now use quantum bits, which are still zeros and ones, but they don't obey the laws of logic, which is man-made law. They obey the laws of quantum physics. So they are fundamentally different than regular bits. And then what we'll discuss is that they are fundamentally more powerful. So now you may ask, okay, what is quantum mechanics? And you keep on talking about those new rules. So here's the two most fundamental rules of quantum mechanics. And then hopefully I'll show you how things are a bit different in the atomic world. So rule number one is what we call the superposition principle. Superposition principle says if I have a quantum particle that can be here or that can be there, then quantum mechanics tells me that my particle, my one indivisible particle, can be both here and there at the same time. Now think of it in terms of information. If I have a bit that can be 0 or 1, then a quantum bit can be in that superposition of both 0 and 1 at the same time. This is not something that we have in a regular computer. Just to show you a little bit the absurdity of the superposition principle. Have you guys ever heard of the Schrodinger's cat? It's very popular now. You know, if you watch Big Bang Theory, they talk about it all the time. Schrodinger's cat was it was a thought experiment from Schrödinger showing how absurd the idea of superposition is in the macroscopic world. You have a cat that is both dead and alive. It kind of doesn't quite make sense. But of course, a cat is not a quantum object. But in the quantum world, we can do that. We do that all the time in our labs at IQC. But that's rule number one. Quantum mechanics also come with rule number two, which says that rule number one works as long as you don't look. So now try to make sense of this. It's kind of hard. Actually, you cannot make sense of this because your experience of the world lives in the classical world. You're not quantum. But you have to make peace with it because ultimately, if you dive down in the fabric of the world, this is how things behave. And these are the new rules that we're going to apply for quantum computing. So I have a little 1-minute video here that I'm not going to go into details of how quantum computer works because I will need a whiteboard and we'll need about 6 hours. 6 hours, 5 times, a couple of weeks. But this gives you the flavor.
By using quantum bits instead of bits, quantum computers can make different, more powerful calculations. Imagine walking around a building. You must move from one corner to the opposite one. But if you don't have to stick to the outside walls, you can get there faster. With quantum computers, these new moves exploit quantum phenomena. There are different paths to get to the right answer and to the wrong answers. Quantum superposition lets them investigate all the paths at the same time. Things need to be choreographed, so paths to wrong answers destructively interfere, while paths to the right answer constructively interfere. This allows quantum computers to solve problems faster.
So this gives you the flavor of how a quantum computer works. And the most important point in this is that they make different moves. So for example, when we did the analogy of moving around a building, right, so if you have to go 10 meters and 15 meters, what we've been doing for the past 70 years is we just started walking faster and faster, but we still had to walk the same amount. A quantum computer, by giving us different moves, we can go right through the building. So the quantum computer could be a little slower. It doesn't have to make as much steps. So we can get to the answer a lot faster. So what is quantum computer good for? What can it do better than a regular computer cannot? So probably the most important application is in the field of quantum simulation. So now you may ask, what do I care about quantum simulation? And on a day-to-day basis, you don't. But quantum simulation is what allows us to understand diseases. It's what allows us to design drugs. It's what allows us to do targeted personalized medicine, to do from the ground up nanotechnology, to understand new types of materials that has an impact across society. Those are very scientific problems with very important societal impact. Nowadays, our computers are notoriously bad at doing quantum simulation. And I mean, they right out suck. we cannot do anything when it comes to quantum simulation. But if we could use a quantum machine to do quantum simulation, it kind of makes sense that we could do that fairly easily. So that's one application, but that's not what I'm going to focus on today because we are at Enterprise World. So I'm going to focus a bit more on the computer science side of things. Quantum computers are very good at search optimization as well as artificial intelligence. And they're also very good at cybersecurity. They're going to have a tremendous impact on cybersecurity. So let's take, for example, there's one algorithm out there called the Grover's algorithm, which is very good at searching unsorted database. So when we talk about big data, which is a very sexy term we have these days, one of the problems is like, how do you search big data? There's so many of it, and our computer needs to sift through all that. Turns out that a quantum computer gives us a quadratic speedup. So what we mean by quadratic speedup is, for example, if you have a database of 1 million entries, normally if you try to find one of them, you have to look, give or take, 1 million times. With a quantum computer, you only need to look 1,000 times, so the square root of 1 million. So now as you grow your database to terabytes and exabytes and petabytes and whatever, a quadratic speedup is quite interesting. Okay? Actually, it can save you hundreds of years on your search. And turns out that unsorted searching is directly related to optimization problem. So when we talk about software development or enterprise software, what do we need optimization problem for? We need optimization for everything. Scheduling. It can be scheduling your distributed computing through the cloud. It could be scheduling of, I don't know, airlines, or just scheduling a meeting with your 5,000 executive employees. But it can help out. It can help out debug softwares. We have quantum algorithms that can help speed up quadratically the software debugging. Voice, image recognition, of course, machine learning and artificial intelligence, which is all based on optimization. So this is where quantum computing can really help out. But this is just a quadratic speedup. You know, it's good, but it's not that impressive. There are other algorithms out there that offers you an exponential speedup. So exponential speedup, it means that you could have problems that will take the time of the universe to be solved, or even longer, and then you can reduce that down to a matter of minutes. So this is what we mean when we say quantum computing can solve impossible problems. And then I focused on one. So I'm going to go a little bit more technical for a second. But if you do any type of deep learning, machine learning, artificial intelligence, one of the approach to do that is to solve a massive system of linear equations, which takes a massive amount of time. This is why right now we do have artificial intelligence. We get better and better and better, but you're not really able to hold a conversation with your computer. Right? If you guys go on Cleverbot and you try to have a conversation, it kind of goes, try it. It kind of goes like, hey. They reply, hey. And you just say, how's it going? Hi, it's going well. Hey, what are you doing tonight? Potato. Right? So, although we've done some great stride, we're not quite there yet, because the computing power needed behind it is so huge that we need to cut corner around. But we have a quantum algorithm that appears, it's not proven yet, this is still very much work in progress, that appears to be exponentially faster. So you could have like a true quantum machine learning or quantum artificial intelligence. And that has application also to big data analysis. And I'm not going to go into the details of why artificial intelligence is important. I think you guys all know it. And the list goes on and on and on. There's another part I want to talk about. That is, I think here there's a lot of business students and computer science students. This is something very important for you. It's on the side of cybersecurity. We live in the connected world. Everything gets exchanged through the net, and especially now with the cloud computing, everything goes on the cloud. We need to make sure that the information that goes out is secure. So we need to protect the information. And also, we need to be able to securely communicate with two parties. But also, you need to authenticate. So you need to make sure that when you're talking to someone, it's not an impersonator. Right? For example, when you get a software update from Microsoft, let's say, or from OpenText, you want to make sure you're talking to them and not somebody else. Also, you need to be able to verify that the data you get is, that has the integrity, that hasn't been tampered with. All of these is based on the idea of cryptography. Cryptography is the science of secret. When you send out your password in the cloud, it's not your password that goes, it's an encrypted version. So nowadays, to encrypt information, we use what we call public key cryptography, and it's based on very, very hard to solve mathematical problem. All of cryptography is based on math. It's just very hard math problem. Such that it's easy to encode, so it's easy for you to encrypt your message, but it's extremely difficult for somebody that doesn't have the key to decrypt. One example of a mathematical problem is factoring numbers. Right? If I take two numbers and I ask you to multiply them together, you can do it very easily, even if the numbers are really big. But if I ask you the reverse, I give you a big number and I say, can you give me the two numbers and multiply together? You cannot do it. Okay? So nowadays we use that big number is about 2096 bits. It will take more than the lifetime of the universe to break that, to factor it. So that's how we rely, that's how our security is, we develop our security. But here's the kicker. Every public key protocol that is deployed out there is vulnerable to a quantum computer. RSA, elliptic curve, AES, all of those that we use day in and day out, that you might not know you're using them, but they are on the back end of everything, we know exactly how to break them with a quantum computer. So this is a bit the downside. Okay? For every disruptive technology, on some good side, there's some downside. But we know about the downside, so it's time to react. So for example, when you build a product, when you build a software product or a suite, well, at some point where there's the exchange of information, of secure information and sensitive information, you need to use protocols like SSL or TLS, or you have to deal with certificate agencies and all this. When you program those products, you have to take that into account. And those protocols relies on crypto system that we know how to break with a quantum computer. So we build a quantum computer, everything that relies on information security just crumbled out. So my goal here is, of course, not to scare you, but just to make you aware. Because you guys are the new generation of computer scientists and business people. You have to be aware of that moving forward. So do you have to worry now? Well, that's a good question to ask, because it depends on a couple of things. So you have to predict roughly when do you think the quantum computer will arrive, in X amount of years. But also, you have to realize, how long do I want to keep my information secure? So if it's a credit card number, you want it secure for 5 years, because after 5 years you get a new card, so you're fine. But if it's trade secret, like corporate strategies, maybe government intelligence, or banking information for an entire enterprise, you want them to be secure a bit more than 5 years. You want them to be secure essentially forever. Now you need to think, okay, how long would it take to change the cryptography protocol? So you might think, it's just a software, I can build that in the weekend. But yeah, the software is easy to build, but then it has to be approved by governments, has to be approved by certificate agencies, it has to be approved by everyone. Last time we did a change in our cryptography protocols, it took 10 years to implement. So we already started at about 10 years. So now if the time to upgrade your crypto system, plus the time you want your information to be secure, if this is longer than the time we think we're going to have a quantum computer, we're in trouble. For credit cards, we're fine now. But for very highly sensitive information, some people think that we're already in trouble right now. So now, is the world as we know it going to start collapsing, and then e-commerce going to stop? Absolutely not. I mean, there are solutions. There are two different types of solutions. One that we call quantum cryptography. Quantum cryptography is actually, it's a hardware solution. We use quantum mechanics to secure information. Remember rule number 2. If you look at it, you destroy the quantum superposition. We can use this to secure information in such a way that anyone trying to eavesdrop will be caught. So anyone trying to look at the communication will create disturbances, and we can keep that. So it is an absolutely secure way of encrypting information. But it's based on hardware, which means we're going to have to change the entire infrastructure of the internet, which could be, one, very long and very costly. The other approach is what we would call the traditional approach. We would still rely on hard-to-solve mathematical problems, but we rely on problems that are known or that are believed to be hard to solve as well on quantum computers. So this is more of a software approach, and this has a lot of, there's already several companies out there that offer that product. So the bottom line is, you need to be aware of those things moving forward. If you are to become the next leader in enterprise software or next leader in product development, you have to be aware of that threat. Because yes, quantum computer offers us a lot of opportunities, but it also, we have to bring back in reality sometime and realize that it can create some danger. So just so you know now, when it comes to quantum-resistant cryptography, it's already out there. The NSA 2 years ago announced that they will no longer take into account any type of protocols that is not quantum resistant. So the people are aware, so the government people are aware. Now we just need to make sure that the private sector is aware as well, because at the end of the day, the private sector would be the one that would be developing those, deploying those, and using those. So when is the quantum computer arriving? Well, the kick with quantum computers is they're extremely fragile to build. The idea of superposition is really, really hard to keep. You can put a particle in two states at once, but any small disturbances or any small interaction with its surrounding destroy that, and then we lose the power of quantum computing. But we are making a lot of breakthroughs day in and day out. Actually, the development is going much faster than we think. Some people estimate that by 2026, we have a chance of 1 out of 7 to have a quantum computer. A usable quantum computers, because we do have small prototypes, they're just not really powerful yet. And then they say that that chance goes up to 1/3 by about 2036. So it's not a question of like, can we build a quantum computer? It's like, no, it's like, when are we going to have it? And there's no one out there in their right mind that truly believes that we won't be able to achieve it. It's just a question of, let's get to work and go through that. So we've been claiming that what we call, quote unquote, quantum supremacy will happen in the next 5 years, and some people even say it's going to happen by the end of the year. What do I mean by quantum supremacy? It's a great term. Us physicists, sometimes we like to be a little dramatic. Quantum supremacy means that we're going to have a quantum computer powerful enough that no classical computer can simulate. So it means that we're entering a realm where we are doing things that cannot even be done on a regular computer. It doesn't matter how big it is. So that doesn't mean that the quantum computer is useful yet, or practical, I would say, but it means that we're starting to enter that. So at that point, once we start re-entering the quantum supremacy, this is where the quantum simulation is going to start popping out, and we're going to be able to start using quantum computing for medicine, drug design, material science, and so on and so forth. The computer science side applications, like the artificial intelligence, code breaking, that might be a few more years down the road. Okay? But the point is, where we are today, quantum computing is not really a science problem anymore. We understand the science. We know where we're going. We know how to build it. It's an engineering problem. So now it's a question of design. The science is figured out. Now we put a chuckload of engineer in the room, and it's all right, now build it, which is a challenge as well. But it's exciting times right now, because quantum computing is truly a paradigm shift. We are using nature to compute. So we are using the most fundamental law of nature to compute. So in some sense, we're unleashing the computing power of nature itself. And a couple little things that I've talked today, AI, searching, code breaking, is really just the surface. It's just what we know what we can do now. And when we're going to realize what we can do in the future will come from people like you, people with fresh ideas. Just like, in 1947, there was 3 people using a computer, and the most optimistic people said, maybe 5 people around the world can use it in 10 years. And now, I have 5 computers just in my bag. Okay? We all use computers because new ideas kept on popping. We did not even foresee the true power of regular computing. Just like right now, we cannot really foresee the true power of quantum computing. But it offers a platform. Just like Bits and Bytes gave us a platform to create all those crazy technologies and software that we have today, now we give you a new platform that we know provably more powerful. We just need to realize what we can do with that. So what does it mean for you as computer scientists and business students? Well, first of all, you need to be aware. This is why I'm here today. I want you to be aware that quantum computing is not only an opportunity, but also a threat. So moving forward, you need to know that. If you are to have a startup company or to become CEO of a big company, you need to know that this is out there and it's gonna change the future of computing and software. Of course, we're gonna need some computer scientists to program those quantum computers. So that's a bit more my way of recruiting you guys. If you want to do grad studies, University of Waterloo, great place for doing quantum computing. But also we need the business people. Because at the end of the day, we're scientists. We know how to solve the science. We have fun solving problems. But we're not business people. So we need business people to identify opportunities and realize how we can take that quantum computing and bring it to the next level and into the marketplace. And this is all going to happen with a generation like you and the generation after you. Thank you very much.